The topic of this lecture and the next one will be linear dynamic systems with random inputs. Well, what we're going to cover is also called linear stochastic systems, and what we're going to do is present the state space models for continuous time linear stochastic systems and discrete time linear stochastic systems. It's important to remember that most engineering systems really are, from physical considerations, continuous time, but our observations are done via sampling, so these are discrete time. Therefore, typically we would start from continuous time models and discretize these. So we'll have both of them covered and the connection between them, which is really the discretization. We'll discuss the Markov property and its implication on these systems. We'll take a look at the propagation equations for the mean and covariance, the first two moments of the state of a linear system driven by white noise. Practically all the results we are going to cover deal with systems driven by white noise, and we have seen earlier in this course how a system which is not driven by white noise can be transformed into a larger system that is driven by white noise by pre-whitening. The frequency domain approach will be shown to connect the power spectral density of a random process, typically either the state or the output of a system, and the state space representation. And we'll illustrate how spectral factorization can be used to pre-whiten an autocorrelated random process and find the appropriate subsystem which, appended to the system, gives an overall new system that is driven by white noise. First, continuous time linear stochastic dynamic systems. The state space model for a continuous time linear stochastic system is x dot of t equal at xt plus bt ut plus dt v tilde of t, where x is a state vector, has dimension nx, u is an input vector or control, a known vector of dimension nu, v tilde is the continuous time input disturbance, also called process noise, and this will be the term by which we refer to it most of the time, or plant noise. It is a vector of dimension nv. Then we have at, the system matrix, possibly time varying, bt, the input gain, possibly time varying, and dt, the noise gain, again possibly time varying. And these matrices A, B, and D are of appropriate dimensions, nx by nx, nx by nu, and nx by nv. And that's again a summary of the designations of these matrices. This is also known as the dynamic equation or plant equation. The state xt is really a linear diffusion process subject to a drift due to this known input which is deterministic. The output of the system is another vector of dimension nz. Z of t is c of t xt plus w tilde of t, where w tilde is the output disturbance or measurement noise. It is not known, it is a model for the uncertainty, the inaccuracies of our observation mechanism. And C, again, might be time varying, even though typically it will be time invariant, is an nz by nx known matrix called the measurement equation. So this is the output equation, or the measurement equation, or the observation equation. Now, if there are no disturbances, there is no v tilde process, no w tilde process. In that case, we are in a completely deterministic case. If we have the initial condition x at some reference time t0 and the input function in the interval t0 to t is the current time, which is denoted as u subscript the interval t0 to t, which is u tau, tau going from t0 to t, we can compute the future output at any time t greater than t0. Z of t will be a function z of the initial state xt0, u in the interval t0 t, the time t, and the time t0. Now, the definition of the state of a deterministic system is the smallest vector that summarizes the past of the system. And this is a complete summary of the past, because it's a deterministic system, which means we can evaluate any future output of the system given the initial state and the intervening input. Now, any linear differential equation that describes an input-output relationship can be put in the form of a first-order vector differential equation. What we have here as state equation is a first-order equation, but for a vector. An nth-order scalar differential equation can be rewritten as a first-order differential equation for an n vector, which amounts to n first-order equations by a suitable definition of the state variables. So what you buy in reducing the order of the differential equation, you have to pay in the need to handle suitably the high-dimensional vector. Now, the initial conditions of the nth order differential equation can be taken as state variables or any invertible linear transformation of them, because they define simply in full the future evolution of the state. Now, if we have a stochastic case, the probability density function of our what used to be the deterministic state vector of the system summarizes the past in a probabilistic sense. So what used to be a state, now we don't know anymore. What we will know is a probability density function, which is a full summary of the past of the system in a probabilistic sense. Namely, we can answer all probabilistic questions. What is the probability density function of future state, future output, and moments, and so on. So the PDF of the state vector is called information state because it summarizes the past in a probabilistic sense under a condition. And the condition is that the process noise has to be white. This is why it is so important to have a dynamic system driven by white noise. Now, the general assumptions about the noises in these stochastic models are as follows. Zero mean, white, and mutually independent. Remember, we have two noises, one in the input, the process noise, one in the output, the measurement noise. If the noise is not zero mean, its mean, if known, can be taken as a known input. So the first condition, zero mean, is essentially not restrictive at all. The second condition is indeed restrictive, as it's the key to being able to solve probabilistically this equation, namely obtain the PDF of the future, any future state given the PDF of the current state. And the two noises also should be mutually independent, otherwise, again, the filtering results rely on this. There are techniques, if they are not independent, again, to transform the problem into one where the standard assumptions, and these are the standard assumptions, are satisfied. So the engineering art in modeling and for engineering analysis is bring your model into the form that can be properly analyzed. And we'll show both how to do the analysis and how to bring more general models into the class for which we have a wealth of tools for analysis. Now, we'll take the continuous time state equation and solve it. It is the equation x dot is ax plus bu plus dv tilde, which has the following solution. Starting from the initial time t0, the value of the vector x at time t is ft t0 times this initial state. ft t0 is the state transition matrix from t0 to t, and typically we write the first argument, the final time, the second argument, the initial time in this case, plus how the input, the known input, and the noise entering into the input affect the system. At time tau, the noise enters v tilde tau multiplied by d tau, the known input u tau multiplied by b tau. This propagates from time tau to time t according to the transition matrix f. 2t from tau is another way of reading this. And then we have to integrate over all the possible values of tau from the initial time to the current time. So this is the solution for the dynamic system we have, which is generally time varying but linear. The transition matrix has a number of properties. Its derivative with respect to the end time is the system matrix eta times the transition matrix as it was. The transition to T2 from T0 is the product of the transition matrix to T2 from sometime T1 and the transition to T1 from the initial time T0 for any time T1. So this is just shows that the transition to T2 can take place as a transition from T0 to an in-between point at T1 and then from T1 to the final time, T2. Furthermore, FTT must be the identity matrix because this is a transition in place, nothing happens. And these last two would also imply immediately that if we go backwards, FTT0 would be the inverse of FT0T. Unfortunately, in general, the transition matrix has no explicit form unless a commutativity property is satisfied. The system matrix times its integral, these two must be, the system matrix and its integral must be commutative, which means this should be equal to the integral times integral of the system matrix times the system matrix. Then, and only then, the transition matrix is the exponential of the integral of the system matrix. There are two important classes for which this condition is satisfied: for time-invariant systems, or within the class of time-varying systems, they have to be diagonal. This is effectively what amounts to decoupled. Each coordinate component of the state vector behaves separately. There is no mutual influence between them. Again, most of the results will be for time invariant continuous time system, which means the A of tau is really a constant A. For a time invariant system, assuming or taking the reference time as 0, f of t, which is f of t and 0, transition to t from 0 is just e to the at. And there are a number of techniques to evaluate the transition matrix. These are computational methods. The first and the most basic one is by just using the infinite series expansion of the transition matrix. E to the at, sum k0 to infinity, at to power k over k factorial, which is the identity matrix, plus at, plus a squared t squared over 2, and so on. This is a numerical method, and it will require obviously truncation of the series unless a closed form expression can be found for each term. Sometimes we can do it. The second method is the Laplace transform method, by just applying the Laplace transform to a time invariant. Remember, Laplace transform works only on time invariant linear systems. You can find that the transition matrix is the inverse Laplace transform of Si minus A inverse. Again, I is the nx by nx transition matrix, identity matrix, and A is the system matrix. This is practical only if one can find the closed form expression of the matrix inverse. Then we can use standard Laplace transform. The inverse explicit can be taken off out of tables. There is a more practical technique called the interpolating polynomial method. And this is as follows. We compute the eigenvalues lambda I of A, and they are I from 1 to NE eigenvalues, where NE is the number of distinct eigenvalues. But the dimension is n by n, it doesn't guarantee that all the eigenvalues are distinct. So we can find a smaller number, only NE of distinct eigenvalues. And the multiplicity of eigenvalue number I will be Mi. In this case, sum of Mi I1 to Ne is the dimension of the matrix N. Then find a polynomial of degree n minus 1, g of lambda, which is sum k0 to n minus 1, some coefficients gk, lambda to the power k. We still have not determined these coefficients, obviously. Now, to find the function that we are interested is e to the at. So we take e to the lambda t. This is the counterpart of the function, the matrix function we are interested, as a scalar. So e to the lambda t would be the counterpart of e to the at. And we would set up a number of equalities. Namely, we say that this polynomial has to be equal to e to the lambda t on the spectrum of A, which says at each eigenvalue, their values must be the same, g of lambda and e to the lambda t at each eigenvalue. And if the eigenvalue is multiple, then derivatives of g must be equal to the corresponding derivatives of e to the lambda t, again, at the eigenvalues. How many derivatives you take? Mi minus 1. Multiplicity is mi. So if it's a single, simple eigenvalue, no multiplicity, then there's no derivative. It's just j equals 0. If it has a multiplicity of 3, then you take the function, first derivative and second derivative, and you equate them. Would these conditions, we have exactly the necessary n equations for the coefficients g sub k. In that case, we have the function g, and now e to the at, the matrix e to the at will be g of A. So this is a polynomial in A now, when we evaluate g of A. Here's an example. Coordinated turn is a motion of an object in a plane with constant speed. Remember, the speed is the magnitude of the velocity vector, and turning with constant angular rate, executing what is called a coordinated turn in aviation language. The constant angular rate vector, velocity vector, will turn at a constant rate, but its magnitude stays constant. The motion equations in the plane with coordinate psi and eta are psi double dot is minus omega eta double dot is omega psi dot, where omega is that constant angular rate for the turn, and omega positive implies a counterclockwise turn to the left. And here we follow the trigonometric convention. In navigation conventions, angles are measured clockwise, so positive turn rate implies a clockwise turn. Now, the state space representation of the above will have a state vector of dimension 4, psi, psi dot, eta, eta dot, will be a linear equation x dot equal ax, and the A matrix is given by, you can see here, this amounts to an integration from psi dot to psi, this from eta dot to eta. So there will be two eigenvalues, 0 and 0, for the integration from velocity to position, and the two purely imaginary conjugate, a pair of conjugate purely imaginary eigenvalues. And obviously this system is not what is called a stable system, because all its eigenvalues in continuous time happen to be on the imaginary axis, not in the left half plane, and that's because of the integration and the rotation. So once the system starts, this equation would go on forever. Now, the result for evaluating the transition matrix is, and suggest to go through the algebraic steps on your own, e to the at would be 1, the sine omega t over omega, 0, minus 1, minus cosine omega t over omega, and so on. What this is convenient is allows easy generation of state trajectories for such terms. The position will evolve exactly along circular arcs, and such terms are common for aircraft, flying objects, or ships also make most of their turns in this manner. They keep their speed, if not exactly, then close to a constant. And it's important to mention that if you would take that original differential equation and you do just a plain brute force numerical integration on it, you will not get an exact circle, which means you go 360 degrees, you will not end up, because of numerical errors, exactly at the same location. This guarantees that you will not be subject to such errors. Now, we are going to connect the concept of a state, which comes from deterministic systems, with the concept of a Markov process. Assume the process noise entering into our state equation, that's the x dot equal ax plus bu plus dv tilde, and we forget about the u component. Perhaps the important thing is the v tilde right now. That's the process noise. This noise is zero, mean, and white. Namely, v tilde of t is independent of v tilde of tau for any t different than tau. In this case, the autocorrelation, that's a white noise, expected value of the vector v tilde times the transpose of it, v tilde prime, is some matrix cap v of t delta t of tau, where this is the Dirac or the impulse delta function. Now, this is not necessarily stationary, because you can see even the mean is 0, this is the autocorrelation, is not time invariant. The whiteness property of the process will allow the preservation of the state's property. Remember, in the deterministic case, the state summarizes in full, completely, the past. If the noise is white, the state still has a property of summarizing the past, but in a slightly different sense. The PDF, the probability density function of the state, at some time t in the future, condition on its values up to an earlier time t1, depends only on the last value xt1. So p of x at time t, given x all the way from minus infinity up to some time t1, and we need the intervening input, obviously, otherwise it's not defined, will be the same as p of xt given only xt1. So the very last point from this interval is all that matters as far as PDF is concerned. So instead of a deterministic summary, the state provides a complete probabilistic summary of the past. Now, intuitively it's important to understand where this comes from. We have white noise. The white noise is completely unpredictable. White is complete independence, in the case what we call strict whiteness, of any future value given the past. So, if the process noise would have been autocorrelated, also called colored, as opposed to white, our equation of summarizing, of the state summarizing in a probabilistic manner the past, that's the Markov property. This would not hold because states prior to T1 could be used to predict future process noise values, V tilde in the interval T1T, and thus X of T in some fashion. If you look at the state equation solution, xt is ft_t1, xt1 plus integral ft tau multiplying b tau u tau plus d tau v tilde tau d tau, indicates that xt1 summarizes the past because this is unpredictable. The input provides the known part of the state's evolution after T1, and the last term in the integral here is the contribution of the process noise, which is completely unpredictable. In other words, the state of a dynamic system driven by white noise is a Markov process. It's very important to understand this both mathematically as well as with physical intuition or engineering intuition.